Hi, I'm Xinhuan Wang, and this talk is based on my published CIPHER paper. And I was inspired by a class project which I built a zip-level socioeconomic indicators dataset, which has income, education level, schools, parks, and such information. And then I trained rig and attributes with sharply additive explanations for predicting housing prices in California. And those models work, but they missed connections and were hard to explain. And housing prices reflect both on neighborhood social level features and transport mobility. And we need maps to tell where the social facts matter and where the transport corridors matter, not just a number or a score. And we need a pipeline that others can repeat and trust. So I built CIPHER: construction, integration, prediction, hypothesis, explanation, and reproducibility, which is a clear and reproducible way to join the social economic indicators and mobility. So first, construction. I turned the city into dots and lines, bike docks, parking meters, and metro stops, and lines are trips and adjacency with sensible geo-limits. And second, about integration, I attach zip-level facts before messages flow, so the context guides learning. And third is prediction, and then it's about hypothesis and explanation. I test the mechanism and then explain the drivers and node and dip levels, and plus a zip share summary. And all runs use the same schema and fix splits or seeds across cities. And here are some details. And in San Francisco and New York, the CIPHER explains about 80% of the variance in price, and that's strong for two very different cities. The leading tab also fits domain intuition. Parking carries access in San Francisco, like metro carries the traffic corridors in New York. And so the model is accurate and its signals match how these cities actually work. And then I checked what models relies on. Firstly, about the hard test, I cut neighborhood links. Predictions shift a lot. We can see the KS is really high. And then for the soft test, I keep lines and attention and only rescale the values. So the curves almost overlap. You can see the KS number is really low. And therefore, we can see that the structure matters and price depends mainly on who connects to whom and not rescaling of the numbers. That makes the evidence more trustworthy. And here is why. We can see the picture in B. Some socioeconomic indicators rank highest, like income, education, and schools. And in picture C, the signal is mixed, like some socioeconomic indicators plus some evening traffic peaks. And then I compress this into dip share, which shows how much of the signal comes from dip level social indicators. And the numbers looks like 5.9% for the San Francisco back, which mostly relies on mobility. And so actions differ by area. For high zip share area, we can invest in schools, parks, or such infrastructure constructions. And for the low zip share area, we can invest in transportation and make it more convenient. And my role, I designed the top city graph, ran the hard and soft props, and built a zip share and fixed schemas for reproducible runs. And here are also some limitations. Firstly, the attributions are not casual, and then some features are static in time. And during my research, I found that population mobility is also affected by some seasonal factors. So next time I'm gonna add time varying flows and origin destination ways and release a small reproducible toolkit for different cities. And thanks for listening.